Let me tell you something that will bother you. I hope it bothers you, because it should. There is an experiment you can do on a kitchen table, more or less, that nobody in the world can explain. Not me. Not Einstein, not Bohr, not anybody who has ever lived. And the experiment is so simple that a child could describe it. You take a wall, you cut 2 slits in it, you throw things at it. That is it. And from that simplicity comes the deepest mystery in all of physics. Now, I am not being dramatic for the sake of drama. I am being careful because people love to talk about quantum mechanics like it is some kind of philosophy, some kind of parlor game, some kind of late-night dorm room conversation about consciousness and reality. It is not a game. It is not a philosophy. It is a warning that nature does not work the way you think it does. And today, I want to show you exactly what I mean. By the end of this talk, you are going to understand what happens in the double-slit experiment. Not vaguely, not with hand-waving. You are going to understand it clearly enough that you will also understand why it is so deeply, profoundly disturbing. And I think that is the honest way to teach it. Do not hide the strangeness. Do not sweep it under the rug with jargon. Face it. That is what a real physicist does. So, let us start with something you know, something comfortable, something from the everyday world. Let us start with bullets. Suppose I have a machine gun. Not a very precise one. It wobbles around. It sprays bullets all over the place, more or less at random. And I aim this wobbly gun at a wall that has 2 narrow slits cut into it, 2 little openings. Behind that wall, some distance away, there is a backstop, a big flat screen like a sandbox that catches bullets and shows you where they hit. I can mark each spot. And after I fire 1,000 bullets, I can look at the pattern of marks on the backstop and ask, what does the pattern look like? Well, think about it. Some bullets go through the left slit. They spread out a bit because the gun wobbles and the slit has some width, and they make a pile of hits behind the left slit. Some bullets go through the right slit. They make a pile of hits behind the right slit, and the total pattern on the backstop is just the sum of those 2 piles. A bump here, a bump there. Maybe they overlap a little in the middle where both slits contribute. But the pattern is smooth. It is just addition. You take the pattern you get from the left slit alone, add it to the pattern you get from the right slit alone, and you get the total pattern with both slits open. Nothing strange, beautiful common sense. And by the way, notice something important. Each bullet goes through one slit or the other, not both. A bullet is a lump of metal. It does not split in half. It goes left or it goes right. And the pattern reflects that simple fact. Good. Now, let us do the same experiment, but with water waves. I have a long, shallow trough of water. At one end, I have a little plunger that bobs up and down and makes ripples. Those ripples travel down the trough and hit a barrier with 2 narrow slits. On the other side of the barrier, the waves come through both slits and spread out. Now, I do not have bullets landing at individual spots. I have waves, and I can measure the intensity of the wave at each point along the back wall. How energetically is the water sloshing at this point? How tall are the waves? And here is the thing about waves that is completely different from bullets. When 2 waves meet, they do not just add up the way bullet patterns do. They interfere. Where the crest of one wave arrives at the same time as the crest of another, you get a very tall wave. We call that constructive interference. They build each other up. Where the crest of one wave arrives at the same time as the trough of the other, they cancel. That is destructive interference. They tear each other down. So on the back wall of the trough, instead of 2 smooth bumps, you get a pattern of alternating high and low intensity. Lots of wave energy here, then nothing, then lots of energy again, then nothing. A striped pattern, an interference pattern. And this pattern is very distinctive. You can tell immediately by looking at it that waves went through, not particles. And I want you to notice something else about the wave pattern. The shape of the interference depends on the spacing of the slits and the wavelength of the wave. If you move the slits closer together, the stripes get wider. If you move them farther apart, the stripes get narrower. If you change the wavelength, the pattern shifts. There is a precise mathematical relationship. And this is important because when we see this kind of pattern, we can work backward and figure out the wavelength of whatever went through those slits. The interference pattern is like a fingerprint. It tells you unmistakably waves went through. Good. So we have our two reference cases. Bullets give you two smooth lumps that add up. Waves give you an interference pattern with bright and dark stripes. And here is the crucial thing I want you to hold in your mind. These two patterns are completely different. You can tell at a glance which one you are looking at. Two smooth bumps, particles. Alternating stripes, waves. There is no ambiguity, no gray area. The patterns are as different as a photograph of a cat and a photograph of a dog. Now I want you to make a prediction. I have not told you the answer yet. I am about to do this experiment with electrons, tiny particles of matter. What pattern do you expect? The smooth bump pattern of bullets or the stripe pattern of waves? Pick one. Hold it in your mind, because the answer is going to surprise you no matter which one you picked. Now, here is where the trouble starts. Here is where everything changes. Let us do this experiment with electrons. Electrons are tiny, tiny things, thousands of times smaller than an atom. And we can build an apparatus that fires electrons one at a time at a barrier with two slits. Behind the barrier, we have a very sensitive detector screen. It could be a fluorescent screen or a CCD plate or some similar device. Every time an electron hits the screen, it makes a little dot, a tiny flash, just one dot at one definite location, like a bullet. The electron arrives as a lump. There is no half electron. There is no smeared out electron. There is no gradual buildup of intensity like a wave. One dot, click, then another dot somewhere else, click. So you might think, well, electrons are just very small bullets, and you fire a lot of them and see what pattern builds up. At first, the dots seem completely random. 10 electrons, 10 dots, scattered around with no obvious order. 100 electrons. Still looks pretty random, but maybe you squint and wonder. 1,000 electrons. 10,000 electrons. And suddenly a pattern emerges that makes your hair stand on end. The pattern has stripes. It is an interference pattern. The same kind of pattern you get with water waves. Bright bands where lots of electrons land, dark bands where almost none land. An alternating pattern of more and less, stretching across the screen. Now wait. Slow down. This is very strange, and I need you to appreciate just how strange it is. Each electron arrives as a single dot, a lump, a particle, one electron, one spot, just like a bullet. But the overall pattern, when you collect thousands of them, is a wave pattern. It is as if each electron somehow went through both slits at the same time and interfered with itself. One electron, two slits, interference. You might say, well, maybe the electrons are bumping into each other. Maybe they jostle each other going through the slits, and the jostling creates the pattern. Maybe they interact with each other in some complicated way. But no, we can turn the source down so low that there is only one electron in the apparatus at a time. One electron leaves the source, travels to the slits, and hits the screen. It makes its dot. Then, and only then, does the next electron leave the source. One at a time. No possibility of interaction between electrons, and the pattern still builds up into those stripes. The interference pattern is still there. One electron at a time. No bumping, no jostling, and yet the pattern that emerges is the pattern of a wave. Let me make sure you feel the weight of this. This experiment has been done not only with electrons, it has been done with neutrons, which are much heavier. It has been done with atoms. It has been done with molecules, big molecules, molecules made of dozens or even hundreds of atoms. The largest molecules ever put through a double-slit experiment, as of when I am telling you this, are truly enormous by atomic standards. And they still show interference. Each one lands at one spot, like a bullet. but the collection shows stripes like a wave. The size of the object does not seem to matter as long as you can keep it from being disturbed by the environment. There is something deeply democratic about this. Nature does not care how big the particle is. The rules are the same for electrons and for molecules. The interference is always there as long as the which path information is not available. And that universality, that democracy, is what tells you this is a fundamental feature of reality, not some quirk of electrons. Let me try another analogy to make sure this lands, because I promised you two different ways to see it. Imagine you have a room with two doors in the front wall. You are going to release a cat at the back of the room and see where it ends up when it walks through one of the doors. If you do this with 1,000 cats, you expect a pattern. Some cats go through the left door, some through the right. The distribution of cats on the other side is the sum of left door cats and right door cats, just like bullets. But in the quantum version, when you are not watching which door the cat goes through, the cats arrange themselves on the far side of the room in a pattern that is impossible to explain unless each cat somehow knew about both doors, as if each cat explored both doors simultaneously and decided where to end up based on information from both paths. And I know that sounds insane. It sounds insane because it violates every intuition you have built up from living in the macroscopic world. But nature does it. That is what happens. That is the experimental result, confirmed in thousands of laboratories around the world. Let me pause here and say it the way I would say it to a bright 12-year-old who just walked in and wants to know what the fuss is about. You fire tiny particles at a wall with two openings. Each particle hits the back screen at one definite spot, like a little bullet. But when you look at where thousands of them land, the pattern has bright stripes and dark stripes, like waves went through, not bullets. Each particle seems to know about both openings. And that, my friends, is the mystery. The only mystery. Now, let me deal with a misconception. A very popular, very widespread, very seductive misconception. People hear about the double-slit experiment and they say, oh, I get it. The electron is a wave when it is traveling, and then it becomes a particle when you detect it. It is a wave-particle duality thing. That sounds neat. It sounds like a nice story, it fits on a bumper sticker, and it is wrong. Or at least, it is dangerously misleading. The electron is not a wave in the way that a water wave is a wave. A water wave is a collective phenomenon. It is millions of molecules of water sloshing up and down together. The wave is the collective motion. But an electron is one thing. There is no collection. There is one electron. When we say the electron behaves like a wave, what we really mean is this. There is a mathematical function, a thing we calculate, called the probability amplitude, and this function obeys wave-like equations. It ripples, it spreads, it goes through both slits, it interferes with itself. But the electron itself, when you look for it, when you detect it, it is always at one place. There is no smeared out electron spread across the screen. There is a dot. So the electron is not a wave that collapses into a particle. That is a fairy tale that has confused generations of students. What is really happening is that the rules governing where the electron will be found, the probability rules, have the mathematical structure of wave interference. The waviness is in the probability, not in the electron itself. The electron is not spreading out like butter on toast and then suddenly snapping back into a lump. The probabilities, the likelihoods, the chances, those are what spread out and interfere. Do you see the difference? It is a crucial difference. Get this wrong, and everything downstream is confused. All right, now comes the heart of the mystery. The part that made Einstein and Bohr argue for the better part of 30 years. The part that I call the quantum warning. What happens if you try to find out which slit the electron went through? You think, well, I am a clever experimentalist. I will just watch. I will put a little detector at each slit, a tiny light source, say. When the electron passes through the left slit, the light scatters off the electron, and I see a flash at the left slit. When it passes through the right slit, I see a flash at the right slit. Now I have which path information. I know which slit each electron went through, and I still collect the dots on the back screen, and look at the pattern. But when you do this, the interference pattern disappears, gone, vanished. Instead, you get two smooth bumps: the boring pattern, the bullet pattern, the pattern of ordinary particles going through one slit or the other. Just by looking at which slit the electron went through, you destroyed the interference. I need you to sit with that for a moment. Let it bother you. You did not change the slits. You did not move the screen. You did not alter the electron source. All you did was gain information about which path the electron took, and the pattern changed. The stripes vanished. The interference was destroyed. And here is the critical part. It is not because your detector was clumsy. It is not because you bumped the electron with your photon and knocked it sideways. People sometimes explain it that way, the Heisenberg microscope argument. And there is something to it, but it misses the deeper point. Even the gentlest conceivable measurement, the absolute minimum disturbance needed to determine which slit is enough to kill the interference. It is not a matter of being more careful. It is fundamental. It is built into the structure of quantum mechanics. The rule is stark. If you can determine which slit the electron went through, there is no interference. If you cannot determine which slit, there is interference. The availability of which path information determines the physical outcome. In the everyday world, watching something does not change what it does. I can watch a baseball fly through the air, and the baseball does not care about my eyeballs. My observation does not alter its trajectory by even an atom's width. But in quantum mechanics, observation is not passive. To observe means to interact. To gain information means to couple your measuring device to the quantum system. And that coupling, that entanglement between your detector and the electron, is what destroys the interference. And let me say something about that word, entanglement, because I used it just now and it is going to come up again. When the detector at the slit interacts with the electron, their quantum states become linked, correlated. If the electron went through the left slit, the detector is in the state saw left. If the electron went through the right slit, the detector is in the state saw right. And these two states of the detector are different, distinguishable. That means the electron's two paths are now labeled, tagged, by the state of the detector. And labeled paths do not interfere. It is as if the universe said, I can tell these two paths apart, so I will not let them interfere anymore. This is a crucial insight. The interference is destroyed not because the electron was kicked or bumped. It is destroyed because the electron became entangled with the detector, and the entanglement makes the two paths distinguishable. Distinguishable paths do not interfere. That is the rule, and it applies with absolute rigor. Now let me walk you through a thought experiment. Step by step, carefully. We set up the double-slit experiment. Electrons going through one at a time. Beautiful interference pattern building up on the screen. Stripes. We are happy. Step 1. We install a detector at the slits, but we leave it turned off. The detector is sitting there, ready, but not operating. What happens? We still get interference. The detector, as long as it is not functioning, changes nothing. Fair enough. Step 2. We turn the detector on. It records which slit each electron goes through. Now the interference vanishes. We get two bumps. The boring pattern, okay. That is what we expected. Step 3. Here is where it gets interesting. We turn the detector on. It records the which path information, but nobody looks at the recording. The data is written onto a tape, a file, whatever, but no human being reads it. The electrons go through, the detector clicks, the information is stored, but no conscious mind examines it. Does the interference come back? No. The interference is still gone. It does not matter whether a person looks at the data. What matters is whether the information exists physically, whether it was recorded by a physical device, whether, in principle, it could be retrieved. If the which path information is out there, written into the state of some physical system, the interference vanishes. Consciousness has nothing to do with it. Let me say that again, because this is one of the most commonly butchered points in all of popular science. Consciousness has nothing to do with it. The moon is there whether or not you look at it. The interference goes away because of physics, not philosophy, because of entanglement between the electron and the detector, not because of some mystical role of the human mind. Anybody who tells you that consciousness creates reality based on the double-slit experiment is selling you something, and what they are selling is not physics. But now, step 4. What if we record the witch path information and then we erase it? Truly, completely erase it, so that it is physically impossible, even in principle, to recover which slit the electron went through? And I mean physically impossible, not just hard. This gets into very deep water. There are real experiments performed in real laboratories called quantum eraser experiments. They were first proposed by Marlin Scully and Kai Druhl in the early 1980s, and they have been performed beautifully since then. And the result is remarkable. If you genuinely erase the witch path information, the interference pattern can come back. Not fully, not straightforwardly, but a subset of the data, when selected properly, shows the interference stripes again. I am not making this up. This has been demonstrated. The interference pattern lives or dies based on one thing. Does the universe contain a record anywhere of which slit the particle went through? If yes, no interference. If no interference, erase the record and the interference returns. This is not philosophy. This is experimental physics, and the quantum eraser experiments get even stranger. There is a version called the delayed choice quantum eraser, where the decision to erase or not erase the witch path information is made after the electron has already hit the screen, after the dot has already appeared. And even then, the choice to erase retroactively determines whether the pattern shows interference or not when you look at the right subset of the data. Let me walk you through how this works, because it is worth the effort. You create a pair of entangled photons. One photon, call it the signal photon, goes toward the double slit and hits the detector screen. The other photon, call it the idler photon, goes off to a separate apparatus far away. Now, the signal photon hits the screen and makes a dot. Done. Finished. Landed. But the idler photon has not yet reached its detector, and the idler photon carries witch path information because it is entangled with the signal photon. Now, at the idler detector, we have a choice. We can measure the idler in a way that preserves the witch path information, or we can measure it in a way that erases the witch path information. We make this choice after the signal photon has already landed. And here is the astonishing part. When we go back and look at only those signal photons whose idler partners had their witch path information erased, we see an interference pattern. When we look at only those signal photons whose idler partners had their witch path information preserved, we see the boring two-bump pattern. The signal photon already landed, and yet its behavior, when sorted by what happened to the idler, changes depending on a measurement made later. Now, I want to be careful here. This does not mean the future changes the past. You cannot use this to send messages backward in time. The interference only shows up when you correlate the data from the two detectors, the one at the screen and the one that did or did not erase the witch path information. Looking at the screen data alone, without the correlation, you see no pattern at all, just a smooth blob. The interference is hidden in the correlations. So there is no paradox, strictly speaking. But it is strange. Very, very strange. So let me tell you what we do know, mathematically, because the math, at least, is clear. In quantum mechanics, we do not describe the world with ordinary probabilities. We describe it with probability amplitudes. An amplitude is a number, a complex number to be precise, that we associate with each possible way something can happen, and the probability of something happening is the absolute square of the amplitude. You take the amplitude, you square its size, and you get the probability. Now here's an important thing about complex numbers, for those of you who have not met them before. A complex number has two parts, a real part and an imaginary part. You can think of it as an arrow in a plane. It has a length and a direction. The length squared gives you the probability. The direction is what allows interference. Two arrows pointing the same way add up to a longer arrow. Two arrows pointing opposite ways cancel to a shorter arrow or zero. That is interference. Now, here is the key difference between quantum mechanics and classical probability. In classical probability, if something can happen in two ways, you add the probabilities. If there is a 30% chance the electron goes through the left slit and a 30% chance it goes through the right slit, the total chance of arriving at a particular spot is roughly 30 plus 30, adjusted for geometry, just addition. But in quantum mechanics, you add the amplitudes first, and then you square to get the probability. And because amplitudes are arrows with direction, they can cancel. If the amplitude for going through the left slit is an arrow pointing up, and the amplitude for going through the right slit is an arrow pointing down, they add up to 0. The probability is 0. No electron ever lands there. Dark stripe. At another spot on the screen, both amplitudes might be arrows pointing right. They add up to a big arrow pointing right. Square it. Large probability. Lots of electrons. Bright stripe. And so on. Across the screen. Bright, dark, bright, dark. That is the interference pattern. It comes directly from the fact that you add amplitudes, not probabilities. And why does the interference go away when you know which slit? Because when you know which slit the electron went through, you are no longer adding amplitudes for two paths. You know it went through the left slit. Fine. You take the amplitude for the left slit path, you square it, that is the probability. Or you know it went through the right slit, you take that amplitude, square it, and you add the two probabilities. No arrows to cancel, no interference. The boring pattern, the rule is simple and devastating. When you cannot distinguish which alternative was taken, add the amplitudes, then square. When you can distinguish, square the amplitudes first, then add. That is it. That is the entire rule. And from that one rule comes all of the strangeness of quantum mechanics. All of it. I sometimes say that the double-slit experiment contains the only mystery of quantum mechanics. Entanglement, tunneling, superposition, the uncertainty principle, all of them are variations on this one theme. If you really, truly, deeply understand what happens at the double-slit, you understand as much about quantum mechanics as any human being can. Now, I want to be careful about one thing. People say the electron goes through both slits at the same time. I have said things like that loosely for the sake of building a picture, but we should be more precise. What we should say is this. There is no experiment you can do that would tell you the electron went through one slit and not the other, without destroying the interference. The question, which slit did it go through, does not have an answer when the interference pattern is present. It is not that the electron went through both slits. It is not that it went through neither. It is not that it went through one and we just cannot figure out which. It is that the question itself does not apply. The question is meaningless in that physical context. Think about it this way. What is north of the North Pole? It is a perfectly grammatical English question. The words make sense individually, but the question has no answer, because north loses its meaning at the North Pole. In the same way, which slit loses its meaning when the conditions for interference are present. And that is the real quantum warning. Nature does not owe you an answer to every question you can formulate in English. Some questions, perfectly sensible sounding questions, have no physical answer. Not because we are ignorant, not because we need a better theory, but because the question does not correspond to any physical reality. This is what drove Einstein to distraction. Einstein believed passionately that the electron must have gone through one slit or the other, and that quantum mechanics was simply an incomplete theory that could not tell you which. He believed there must be hidden variables, deeper properties of the electron that we had not discovered yet, that would restore a complete deterministic picture. He and Bohr argued about this for decades. Magnificent arguments, thought experiments of extraordinary ingenuity. Einstein would propose a way to beat quantum mechanics, and Bohr would find the flaw, again and again. Now, let me tell you about one of their most famous exchanges, because it illustrates the point beautifully. Einstein proposed what is now called the EPR argument, named for Einstein, Podolsky, and Rosen. The idea, in simplified form, goes like this. Make two particles that are entangled, correlated in a quantum mechanical way. Send them off in opposite directions, far apart. Measure one particle. Because of the entanglement, you instantly know something about the other particle, but you did not touch the other particle. You did not disturb it. So, Einstein argued that property must have existed before you measured it. It must have been a real, definite property of the particle all along. Therefore, quantum mechanics, which says the property is not definite until measured, must be incomplete. Bohr's response was subtle. He argued that you cannot separate the two particles so cleanly. The entanglement means the two particles are part of one quantum system, and measuring one is inseparable from the state of the whole system. The question, what is particle B doing before I measure particle A, is another one of those questions that does not have an answer. For decades, this was considered a philosophical disagreement. Two brilliant men arguing about the meaning of a theory, not about its predictions. Then, in 1964, John Bell, a quiet, careful Irish physicist working at CERN, changed everything. He proved a mathematical theorem, Bell's theorem, that showed any theory with hidden variables of the type Einstein wanted would make predictions different from quantum mechanics in certain carefully designed experiments. Not different by much, but different, measurably different. And Bell showed exactly what experiments to do and what numbers to compare. This turned a philosophical debate into an experimental question. You could go into a laboratory and ask nature to settle the argument. And nature is always willing to settle arguments if you ask politely and carefully enough. And the tests have been done, starting with the pioneering work of Alain Aspect and his colleagues in Paris in the early 1980s. They used pairs of entangled photons and measured their polarizations at various angles, just as Bell had prescribed. And the results violated Bell's inequality. The correlations were too strong to be explained by hidden variables. Nature sided with quantum mechanics, not with Einstein. Since then, the experiments have been repeated many times, by many groups, with increasing sophistication, closing loophole after loophole. The detection loophole, the locality loophole, the freedom of choice loophole. One by one, they have all been addressed. And every time, the result is the same. Quantum mechanics wins. Bell's inequality is violated. Nature really is this strange. But let me be fair, because fairness matters in science. There are different interpretations of what all this means. The Copenhagen interpretation, roughly Bohr's view, says that quantum mechanics is a tool for calculating probabilities of measurement outcomes, and you should not ask what is really happening between measurements. The quantum state is not a description of reality. It is a description of our knowledge. The many worlds interpretation, due to Hugh Everett, says that the electron really does go through both slits, in a sense, because the universe splits. In one branch, it went left. In another, it went right. Both outcomes are real. Both branches exist. They just do not interact with each other, which is why you only experience one outcome. The pilot wave interpretation from Louis de Broglie and David Bohm says the electron is a real particle that goes through one slit, always just one, but it is guided by a wave that goes through both slits. The wave sets up the interference pattern, and the particle rides the wave to its final position. Each of these interpretations gives the same experimental predictions. They agree on what you will observe. They disagree, sometimes violently, on the story you tell about what is happening behind the curtain. And as of now, we do not have a way to experimentally distinguish between them. Some of my colleagues get very emotional about their favorite interpretation, as if it were a matter of life and death. I think they should calm down a bit. The physics is the same. The equations are the same. The predictions are the same. What I want to emphasize is that the mystery of the double-slit experiment is not resolved by any interpretation. Every interpretation has something profoundly strange in it. Copenhagen tells you to shut up and not ask what is really happening. Many worlds asks you to accept an infinity of parallel universes, each as real as this one, splitting off at every quantum event. Pilot waves require a non-local guiding field that you can never observe directly and that propagates influences faster than light. Pick your poison. Nature is strange at this level, and no clever narrative makes the strangeness disappear. Let me go deeper still. Let me tell you about the connection between the double slit and entanglement, because they are the same mystery wearing different masks. We talked about what happens when you put a detector at the slits and measure which path the electron takes. The interference goes away. But what if the detector is not at the slits? What if it is somewhere else entirely? There are experiments where you create pairs of particles, entangled particles. You send one toward the double slits and the other off to a separate detector, far away, miles away if you like. And by measuring the distant particle in a certain way, you can determine which slit the nearby particle went through, and when you can do that, the interference pattern for the nearby particle disappears. Even though no one placed a detector at the slits, even though no one touched the particle going through, the information about its path was available over there, far away, and that was enough. This is quantum entanglement applied to the double slit. Einstein called entanglement spooky action at a distance, and he did not mean it as a compliment. He meant it as an accusation. He was saying, look how absurd this theory is. It requires instantaneous connections across space. But the experiments have been done again and again with ever greater rigor, and the correlations are exactly as quantum mechanics predicts. And notice how this connects back to our central theme. The interference pattern at the double slit depends on the unavailability of which path information. It does not matter where that information is stored or how it was obtained. If it exists anywhere in the universe, encoded in any physical system, the interference is gone. The universe keeps very strict books. Now, I want to talk about why we do not see this strangeness in everyday life. You do not see baseballs making interference patterns. You do not see cats going through two doors at once. Why not? If quantum mechanics is the fundamental theory, and if it applies to everything, then why is the world not a shimmering blur of interference and superposition? The answer has a name: decoherence. A baseball is not a simple quantum system. It is made of something like 10 to the 25th atoms, and it is constantly interacting with its environment. Air molecules bounce off it, tens of billions per second. Photons of light reflect off its surface. Thermal radiation bathes it from all sides. Each one of those interactions is, in effect, a tiny measurement. Each air molecule that bounces off the ball carries away a little bit of information about where the ball is and where it is going. And what have we learned? When the which path information is available, the interference vanishes. Well, for a baseball, the which path information is available in extraordinary abundance. Trillions upon trillions of air molecules know where the ball is. The environment has measured the ball's position with staggering precision. And so the quantum interference, the stripes, the waviness, the superpositions are destroyed, not because quantum mechanics stops working, quite the opposite. Because quantum mechanics is working exactly as it should. The interference is killed by the flood of environmental measurements. This process, decoherence, is not something separate from quantum mechanics. It is a consequence of quantum mechanics applied to big systems in warm environments. A big object cannot maintain quantum interference because the environment is constantly extracting which path information. And the bigger the object and the warmer the environment, the faster this happens. For a baseball in air, the decoherence time is something like 10 to the minus 30 seconds. Unimaginably fast. The quantum coherence is gone before it could ever possibly matter. So the classical world, the world of definite positions and predictable trajectories and solid tables and reliable clocks, is not a separate realm from the quantum world. It is the quantum world, seen through the blurring effect of trillions of environmental interactions. We live in a quantum universe. We always have. The classicality is an approximation, an extremely good approximation for big things, but an approximation nonetheless. Think of it this way. Imagine you are standing next to Niagara Falls. The roar is so loud you cannot hear a single droplet, but the roar is made of droplets. Every bit of that thunder is the sum of individual splashes. In the same way, the classical world is made of quantum events. The individual quantum weirdness is there, at the foundation of everything. But it is drowned out, decoherent, washed away by the noise of the environment. This is why the double-slit experiment has to be done with tiny particles in controlled environments. Not because quantum mechanics only applies to small things. It applies to everything. But small things, carefully isolated from the environment, can maintain their quantum coherence long enough for us to see the interference. A single electron in a vacuum, shielded from disturbances, can show you the stripes. A baseball cannot. Not because the baseball is classical, because the baseball is quantum, but decoherent. Let me come back now to the path integral formulation, because it gives a beautiful picture of what is going on, and it is the framework I am perhaps most associated with. In this framework, we imagine that when a particle goes from point A to point B, it takes every possible path, I mean every possible path, through the left slit, through the right slit, around the building, to the edge of the galaxy, and backward in time, and then forward again, every conceivable trajectory, no matter how absurd, and we assign an amplitude, a little arrow, to each path. The direction of the arrow depends on the action, a quantity from classical mechanics that describes how costly a path is, in a sense. Paths with very different actions have arrows pointing in very different directions, and we add up all the arrows. Now, most of those paths are wildly different from each other, and their arrows point in wildly different directions. They cancel. They add to nearly zero. But the paths that are near the classical path, the path that Newton's laws would predict, those paths have arrows that nearly line up. They add constructively, so the total amplitude is concentrated near the classical path. That is why, in ordinary life, things move along classical trajectories. The quantum amplitude is overwhelmingly concentrated there. But at the double slit, something special happens. There are two bundles of nearby paths, one through each slit. Both bundles contribute significantly. Their amplitudes do not cancel, and the amplitudes from the two bundles can interfere with each other. At some spots on the screen, the arrows from the two bundles line up bright stripe. At other spots, they cancel dark stripe, interference pattern. I find this picture deeply satisfying. It says that the universe is not deterministic in the old Newtonian sense. Every path is explored. Nothing is excluded in advance. But the laws of physics, through the mathematics of amplitude addition, select which paths contribute and which cancel. It is like a democracy of possibilities, with the laws of physics counting the votes. But even this beautiful picture does not answer the deep question. It does not tell you what the electron is really doing. The path integral is a calculation method, an extraordinarily powerful one. It gives the right answers. But the question, what is the electron doing when nobody is looking, that question remains open, unanswered, and perhaps unanswerable. And this brings me to the biggest lesson of all, the lesson I most want you to carry with you when you leave. Everything is quantum. Everything. The chair you are sitting in, the air you are breathing, the light hitting your eyes, your brain, your thoughts, insofar as they are physical processes in neurons. All of it, without exception, is governed by quantum mechanics. The classical world you think you inhabit is a derived phenomenon. It emerges from quantum mechanics through decoherence, through the ceaseless measurement performed by the environment. And let me tell you what this means in practical terms, because quantum mechanics is not just philosophy. It is the most useful theory ever devised. Every transistor in every computer chip operates on quantum principles. Without quantum mechanics, there are no transistors. Without transistors, there is no electronics, no radio, no television, no computing machines. The entire technological infrastructure of modern civilization rests on the principles that the double-slit experiment reveals. Lasers work because of quantum mechanics. The stimulated emission of radiation, which is what the word laser stands for, is a purely quantum phenomenon. Every laser pointer, every fiber optic cable, every surgical laser, every compact disc player is a quantum device. The stability of matter is a quantum mechanical fact. Why does a table support your coffee cup? Why does it not collapse? Because the electrons in atoms obey quantum rules that prevent them from falling into the nucleus. Without quantum mechanics, atoms would be unstable and solid matter would not exist. You would not exist. Chemistry, all of chemistry, is quantum mechanics applied to atoms and molecules. Every drug, every plastic, every material, every reaction in your body is governed by quantum rules. the way hemoglobin grabs oxygen, the way chlorophyll captures sunlight, the way DNA replicates, quantum mechanics, all of it. So when I say the double-slit experiment is important, I do not mean it is important the way a painting in a museum is important. I mean it is important the way the foundation of a building is important. Take it away, and everything collapses. The double-slit experiment pulls back the curtain. It shows you the gears and wheels behind the stage set of everyday life. And what you see is that reality is not made of little hard balls bouncing around according to Newton's laws. It is made of something more subtle, something described by probability amplitudes, something that interferes and entangles and refuses to be pinned down until you force the issue by measuring. And that is my quantum warning, the warning I want to leave you with. Do not let anyone tell you they understand this. If they tell you they understand quantum mechanics, they have not thought about it hard enough. What we can do is use the theory brilliantly, successfully. Quantum electrodynamics gives predictions accurate to better than 10 parts in a billion. That is like measuring the distance from New York to Los Angeles and being correct to the thickness of a human hair. The theory works. It works better than anything else in the history of science. But we do not understand why it works. We do not understand why nature chose probability amplitudes instead of ordinary probabilities. We do not understand what measurement means at a fundamental level. We do not understand what happens between measurements. And we may never understand. That is the honest truth. And I think honesty is more valuable than comfort. But here is the beautiful part, the wonderful, exhilarating part. Not understanding does not mean we cannot make progress. Science is not about having a comfortable mental picture that matches your intuition from throwing baseballs and picking up groceries. Science is about predictions, patterns, equations that match experiments. And quantum mechanics does that better than any theory ever conceived by human beings. So we use it. We use it joyfully, carefully, with our eyes wide open and our sense of wonder intact. We do not pretend the strangeness is not there. We do not paper over it with false explanations or mystical nonsense. We acknowledge it, we respect it, and we keep working. The experiment is simple. 2 slits in a wall, fire particles through. Look at the pattern. But from that simplicity, the entire mystery of the universe unfolds. The wave nature of probability, the role of information, entanglement, the emergence of the classical world, the debate between the greatest minds of the 20th century, the foundations of every piece of modern technology, all from 2 slits. And I think that is perhaps the most astonishing thing of all. Not the strangeness itself, but the fact that such a simple experiment can reveal it. You do not need a particle accelerator the size of a city. You do not need a telescope pointed at distant galaxies. You do not need a billion-dollar satellite. You need a wall with 2 holes in it and something to throw at it. And nature shows you its deepest secret. I find that incredibly generous of nature. It does not hide the mystery behind impossible barriers. It puts it right there in the simplest possible experiment, as if it wants you to find it. So the next time someone asks you, do you understand quantum mechanics? You can say with complete honesty, no, but I understand why I do not understand it. And I know that the strangeness is not a bug. It is a feature. It is the deepest feature of the universe we inhabit. And that, I believe, is the beginning of real knowledge. I want to hear what you think. If the electron does not have a definite path through the slits, and the question which slit has no answer, does that trouble you or does it excite you? Write it down and tell me.